Alright, our top graph here we have y equals sine x. You can tell that because it's starting at 0, sine of 0, 0, and the amplitude is 1, and the period is 360 degrees. Alright, now we are going to find the gradient all the way of the tangent all the way along this graph. Now the gradient right here you can see is 0. The gradient right here is 0. So we're going to graph the gradient function on top of this. You might remember this from prelim. So if our gradient at the top of this curve here at this turning point is 0, then on the gradient function it's just going to be here. It's going to be an x-intercept. And similarly, just down here where the gradient and the tangent is 0, it's going to be, our gradient function is going to have an x-intercept right there. Now all the way along here you can see the gradient is positive, which means our gradient function is going to be above the x-axis. And all the way down this section of the curve, our gradient function is negative, which means our gradient function is going to be below the x-axis. So from x equals 90 to x equals 270, our gradient function is below the x-axis. So you could say it is like this. And then on this section of the curve between 270 degrees and 360, you can see it's positive. The gradient is positive, so our gradient function is going to be above the x-axis, and then same with just here. And what do you know? It looks like the gradient function of sine x looks like cos x. So that's pretty cool. Let's see what happens when we draw the gradient function down here on, you can see that blue graph there is y equals cos x. Okay, so we can see where the gradient of the tangent would be equal to 0 right there. So let's graph that on our gradient function just there. What else can you see? I might make that pen a bit bigger. Okay, you can see all the way from here to here, from 0 to 180 degrees, the gradient is negative. So our gradient function is going to be below the x-axis. And from 180 degrees all the way up to 360, our gradient function is positive. So the graph of our gradient function is going to be above the x-axis. You can also see right here on the graph, our tangent is 0 as horizontal. The gradient of the tangent is 0. So on our gradient function, that's another point there where the gradient function is 0. And likewise right here at 360 degrees, the gradient of that tangent is 0. So on the graph of our gradient function, it's going to go through 0. So from 0 to 180, the gradient is negative. So our graph of our gradient function will be below the x-axis. And from 180 to 360, the gradient is positive. So our gradient function will be above the x-axis. And isn't that great? You can see now that the graph that we've just drawn is y equals negative sine x. So that means the derivative of cos x is negative sine x. So that is in this table here. So the derivative of sine x is cos x. The derivative of cos x is negative sine x. And this is a new one. The derivative of tan x is sec squared x. Now remember that tan x is equal to sine on cos. So if you say that tan x equals sine x on cos x, you can use the quotient rule to differentiate this. Using the quotient rule, we would say u equals sine x, u dash equals the derivative of sine x, which you've just discovered is cos x. V is the denominator, that's cos x. And v dash is the derivative of cos x, which you've just discovered is negative sine x. So using our quotient rule, the derivative of tan x is going to be the insides, cos squared x, minus the outsides. Sine x times negative sine x is positive, so negative sine squared x, but with that negative there, turns that into a positive, all over v squared. Now v is cos, that's going to be all over cos squared x. Now you can see cos squared x plus sin squared x is 1. That's one of those trig identities we learned in prelim. So 1 over cos squared x, and the derivative of cos squared x is x squared x. So that's how we get the derivative of tan x is x squared x. So if you can see as well here, in these rules here, the derivative of sine ax, if there's a coefficient in front of x, then that differentiates to a cos ax, where a is the derivative of ax. So you can see that that angle there, ax, still remains the same. Same with here, the derivative of cos ax, this becomes negative a sine ax, just like how here the derivative of cos is negative sine. It's negative, where also a is the derivative of ax, and the angle is still exactly the same. And the derivative of tan ax is going to be a sec squared ax. It's the same kind of reasoning. So if you just replace the ax with f of x, some function, then you're going to get f dash x cos f of x. Okay, so you just have to remember that the derivative of sine is cos, the derivative of cos is negative sine, and the derivative of tan is sec squared x. So these rules have been printed out for you. Examples and put that into practice. So the derivative of tan 3x. So f of x here is 3x. The derivative of 3x is just 3. So we could write this as y dash equals 3 sec squared 3x. Because remember the angle 3x just stays the same. In number 2 here now, y dash equals. So the derivative of x on 2 is just half, because that's just another way of writing half x. And remember the derivative of cos is negative sine, so that's going to be negative half sine x on 2. Okay. Number 3 here now, there's our f of x. And the derivative of that, of 1 minus 2x, is just negative 2. Okay, the derivative of sine is cos, and we're going to keep that angle exactly the same. So our derivative is negative 2 cos of 1 minus 2x. Now next example here, f of x is x cubed minus 1. The derivative of x cubed is 3x squared. The derivative of sine is cos, and you'll keep that function exactly the same. Okay, starting to see the pattern here. Number 5, the derivative of 2 sine x. So remember the graph of 2 sine x would just be very similar to sine x. If this, say, was sine x, then 2 sine x would have an amplitude 2. Yeah, and then the derivative of that you can see is just going to be 2 cos x, similar to the very first graph I drew today, because the derivative of sine x is just cos x, and that constant out the front is just going to remain the same. Okay, now we've got the derivative of tan of negative x. So the derivative of negative x is negative 1. And the derivative of tan is sec squared. So it ends up being negative sec squared of negative x. Remember, we're keeping that angle exactly the same. That's f of x. Okay, number 7 and 8. They look very similar, don't they? It just depends on where you put that little square. It changes the meaning of the equation. Sine of x squared means f of x is x squared. So f dash x is going to be 2x. The derivative of sine is cos, and we're keeping that angle exactly the same. Whereas y equals sine squared x, that's just a better notation for writing y equals sine of x all squared. They mean the same thing. And remember when we were differentiating, this is like a function of a function. You bring the power down the front. So 2 comes down the front here. You keep the bracket the same, subtract 1 from the power, and you times by the derivative of what's inside the bracket. So the derivative of sine x becomes cos x. So this becomes 2 sine x cos x. You don't really need those brackets there. You just write it like this. Y equals 2 sine x. Oops, missed my x there. 2 sine x cos x. Okay, and here in number 9 we have another function of a function rule, just like 8. So we are going to bring the power down the front. So 9 is going to come down the front. Keep the brackets the same. Subtract 1 from the power. And times by the derivative of what's inside the brackets. So the derivative of 2x plus tan 7x is going to become 2 plus, and now the derivative of tan 7x is 7 sec squared 7x. Okay, and I guess there's no really way that we can simplify that. I'm not going to expand that out at all. Alright, number 10, y equals x squared sine x. There's a function there of x, and there's another function of x, and they've been multiplied together. So we are going to need to use the product rule to differentiate this, where u equals x squared, u dash equals 2x, v equals sine x, and v dash equals cos x. So our derivative becomes insides 2x sine x plus the outsides, which is plus x squared cos x. And you can either leave your answer like that, or you can factorise out this common x here, which is common. Either would be fine. Doesn't say you need to factorise, so just that answer there is perfectly okay. In number 11, we've got a function divided by another function, or we've got the quotient of two functions. So we're going to use the quotient rule to differentiate this, where u equals tan x, u dash equals sec squared x, v equals x, and v dash equals 1. So our y dash is going to be insides x sec squared x minus outsides tan x all over the denominator squared x squared. That can't be simplified any further, so we'll just leave it like that. Although we could change sec squared to 1 on cos squared, and we could change tan x to sine x on cos x. Look for a common denominator there, but what we've got there is perfectly okay. Okay, number 12. Find the equation of the tangent to the curve y equals tan 3x at the point pi on 3 is 0. So you might remember finding the equations of tangents and normals when we did the topic last year on geometrical applications of calculus. We have to differentiate this function, and we have to find the gradient at this point, x equals pi on 3. Then we'll have the gradient at this point, and we have the point, and we're trying to find the equation of the tangent. The tangent is a straight line. For finding the equation of a straight line, we've got a point. We'll have the gradient. Once we substitute pi on 3 into the gradient function, then we can use the point gradient formula to find the equation of the tangent. So let's differentiate to find the gradient function. So if y equals tan 3x, then y dash equals 3 sec squared 3x. And let's find what that gradient is at the point x equals pi on 3. That is our point here. So at x equals pi on 3, our gradient, y dash, equals 3 sec squared, and we're going to substitute in 3 times pi on 3, which is 3 times pi on 3. You can see the 3's there are going to cancel, so that's 3 sec squared pi. Now, sec squared pi means 3 times 1 on cos squared pi. We could even write that as 3 over 1 on cos squared pi. Alright, cos of pi. You can do that by either using the unit circle or knowing the cos graph. Let's use the unit circle. So remember, cos of pi. Pi is over here. What is the coordinates of this point here? The coordinates of that point is -1, 0. And remember, cos is the x coordinate and sine is the y coordinate. So this is saying cos of pi is -1 and sine of pi is 0. Another way is if you were to draw the cosine curve like that. There's 2 pi. Halfway is pi. You know the amplitude, that's 1, and that value there will be -1. And then you can see cos of pi is -1. Alright, so we've got 3 over -1 squared. And -1 all squared is +1. So this is going to equal 3. So our gradient of the tangent at this point, pi on 3, x equals pi on 3 is 3. So now we have our point and we have our gradient. So we're going to use the point gradient formula to find the equation of the tangent. So y minus y1 equals m outside of x minus x1. You might remember that is the formula. So we're going to have y minus y1, which is 0, equals m, which is here, our 3, outside of x minus, there's our x1, y1, pi on 3. Alright, so we're going to get y equals 3x, expanding the brackets, minus pi, or putting it in general form, 3x minus y minus pi equals 0. So there's the general form of the equation of our tangent at the point x pi on 3, 0 on the graph, y equals tan 3x.